For the last 2 decades, astronomers have been investigating a grand cosmic crime, a theft of vast proportions. The case is simple. Half of the entire universe is missing. Now, before you say dark matter, let me be clear. We are not talking about dark matter, which is a separate mystery, 27% of the cosmos. And we are not talking about dark energy, 68%. We are talking about this, normal, ordinary baryonic matter, the stuff of protons and neutrons, the matter that builds you, me, the planets, and every star you can see. For decades, our most fundamental theories have insisted that this normal matter must make up 5% of the total universe. And yet, when we went looking, when we counted every star, every galaxy, every puff of gas we could find, we only found 2.5%. Half of everything that is real had vanished. Today, we are reopening the cold case of the missing Baryon problem. We will lay out the evidence, follow the failed investigations, and reveal the surprise eyewitness that finally, after 20 years, broke the case and found the missing half of the universe. In any missing persons case, you must first prove the victim existed. How are we so sure the universe should have 5% normal matter? The answer is that the universe left us a receipt. In fact, it left us two independent, unforgeable fingerprints from the moment of its birth. Our first piece of evidence comes from the first 20 minutes of time. In the beginning, the universe was a scorching hot soup of protons, neutrons, and radiation. It was too hot for atoms to form. Specifically, it was too hot for deuterium, a single proton and neutron bound together. As the universe expanded and cooled, protons and neutrons tried to fuse, but to make stable helium-4, they had to pass through the deuterium bottleneck. The problem was, high-energy photons would blast the fragile deuterium apart as soon as it formed. This went on for minutes, but the rate at which they were blasted apart versus the rate they could fuse depended on one critical factor: density. The denser the soup of matter, the baryon density, the easier it was for protons and neutrons to find each other, fuse, and burn the deuterium into helium before it could be destroyed. By 20 minutes, the universe was too cool for any fusion. The reactions were locked in. Therefore, the amount of deuterium left over is a perfect snapshot of the universe's original density. When we look at the oldest, most pristine gas clouds in the distant universe, we measure that ratio: 26 deuterium atoms for every million hydrogen atoms. When we plug that number into our BBN models, it spits out a precise answer. To get that ratio, the total density of normal baryonic matter must be 5% of the universe. Our second piece of evidence is even stronger. It is the baby picture of the universe, taken at 400,000 years old, the CMB. This isn't just a pretty map of hot and cold spots. This is a sound map. The early universe was filled with plasma, and sound waves, or pressure waves, rippled through it, created by gravity and radiation pressure fighting each other. When we look at the acoustic peaks in the CMB data, the harmonics of the universe's first song, we can measure the ratio of the different ingredients. The ratio between the first and second peaks on this graph tells us with ironclad certainty the ratio of baryons to photons. And the answer? Exactly 5%. The evidence is undeniable. Both BBN and the CMB, two separate gold standard methods, agree. the universe was born with 5% normal matter. So, if it existed, where did it go? The search began in the late 1990s. Astronomers started a cosmic census. The first step was easy. Add up all the glowing matter, all the stars in all the galaxies. The result was a shock. This accounted for less than 10% of the 5% we were looking for. Most of our universe was not in stars. So, where was it? The logical next step was to look for cold, dark gas, the stuff between the stars. But how do you find gas that doesn't glow? You use a backlight. This brings us to the first great search technique, the Lyman-alpha forest. Investigators used quasars, the brightest objects in the cosmos, the accretion disks of supermassive black holes, as their searchlight. As the light from a distant quasar travels billions of light years to Earth, it passes through vast ancient clouds of neutral, cold hydrogen gas. This cold gas absorbs the quasar's light at one specific frequency, the Lyman-alpha transition. The result is that the quasar's smooth spectrum arrives at Earth looking like a barcode. It's filled with thousands of little black absorption lines. This is the Lyman-alpha forest. Each line is a fingerprint of a cloud of cold gas we pass through. By counting these lines, scientists could finally weigh the cold, dark gas between galaxies. This search was a huge success. It found a massive amount of missing matter. When this forest was added to the census, our total amount of found matter jumped to 50%, half. In the early 2000s, the case went cold. We had found half of the missing matter in these cold intergalactic clouds. But the other half, 2.5% of the entire universe, was still completely, totally missing. The investigators had found all the cold gas. This led them to a new, terrifying suspect. What if the missing matter wasn't cold? What if it was hot? This is where computer simulations took over. Cosmologists built entire universes inside supercomputers, like the Illustrious simulation, to see where matter should have gone. The simulations were unanimous. They showed that as galaxies formed, their gravity acted like a cosmic web, pulling matter together. But as this matter fell toward the galaxies, it was shock-heated to incredible temperatures, 100,000 to 10 million Kelvin. The simulations predicted the missing 50% of our matter was hiding in this state, a diffuse, searingly hot fog floating in the vast filaments of the cosmic web, connecting the galaxies. They gave this suspect a name, the Warm-Hot Intergalactic Medium, or WHIM. The WHIM was the perfect suspect. It was designed to be invisible. It was too hot for the Lyman-alpha forest. At these temperatures, hydrogen is ionized. Its electron is ripped off. A hydrogen atom without an electron cannot absorb Lyman-alpha light. It was a ghost to the quasar searchlight. And at the same time, it was too cold and diffuse for our X-ray telescopes. Hot gas does glow in X-rays, but the WHIM was so spread out, just a few atoms per cubic meter, that its signal was hopelessly faint, lost in the background noise of the cosmos. The case was stalled. We had a suspect, the WHIM, but no way to find it. We had no eyewitness who had seen it, until 2007. In 2007, astronomers found something new, a single, bizarre pulse of radio waves lasting just a few milliseconds. It was impossibly bright, and it came from deep space. They called it a fast radio burst, or FRB. We still don't know what causes them. The leading theory is they are the death screams of magnetars, the zombie stars we've discussed before. But for this case, what they are is less important than what they do. They are the perfect instantaneous flashbulb from across the universe, and they gave us the eyewitness we needed. To understand how, we need to talk about dispersion. When a sulc of light travels through a plasma, a soup of free electrons, the plasma acts like a cosmic prism. It slows the light down, but it slows low-frequency light, like red, more than high-frequency light, like blue. The FRB flash is a pulse of all radio frequencies at once. But as it travels for billions of years through the WHIM, the very plasma soup we're hiding, its signal gets smeared. The high-frequency radio waves arrive at Earth first. The low-frequency waves, slowed down by all those electrons, arrive a fraction of a second later. The pulse that left as a bang arrives as a descending beow. Think of the Whistler effect from lightning in the sample script. This smearing is called the dispersion measure, DM. And here is the eureka moment. The amount of smearing is a direct count of the total number of free electrons the signal passed through. It is a direct count of the missing baryons. The FRB is the eyewitness. It travels through the dark, invisible filament of the WHIM, and when it arrives, its testimony is written in its smeared-out signal.
The FRBs gave us the method, but we needed a conviction. The problem was, for years we couldn't tell how far away the FRBs were. We didn't know the distance to the crime scene. But in 2017, that changed. A team led by Australian astronomer Jean-Pierre Macquart began to pinpoint the FRBs to their host galaxies. For the first time, we had both pieces of evidence for the trial, the dispersion measure and the redshift, or distance. The team began to plot the data. On the x-axis, they put the distance. On the y-axis, they put the dispersion measure. If the WHIM was not real, if the missing matter was not out there, the graph would be a random scatter plot. But if the WHIM was real, if the missing baryons were really spread evenly throughout the cosmos, the graph would show a perfect straight line. The further the FRB, the more smearing it would have. In 2020, they published their paper in the journal Nature. The result? A perfect straight line. The slope of that line, the Macquart relation, is a direct measurement of the average density of matter in the universe. And when they calculated that density, it came out to 0.05 baryons per cubic meter. It was the exact number, the 5% density predicted by the Big Bang all those decades ago. The case was closed. The verdict was in. The missing half of the universe had been found. It was not hiding in dark stars. It was not locked away in exotic objects. It was exactly where the simulations said it would be, in the WHIM. The vast majority of the normal matter in our universe, the stuff we are made of, is not in the bright, beautiful galaxies we see. It is in the dark, hot, invisible nothingness in between them. The stars and galaxies, they are just the foam on the wave, the bright, dense points where the great cosmic web has collapsed. The story of the missing baryon problem is a triumph of scientific investigation. It's a case where the prosecution, the BBN and CMB, laid out a case so strong we knew the victim existed even when we couldn't find it. It's a case where our detectives, the computer simulations, told us exactly who the suspect was and where it was hiding. And it's a case where a new, mysterious eyewitness appeared at the last minute, providing the final, irrefutable testimony needed to close the books on one of the greatest mysteries of the cosmos. We've closed the case on the missing baryons, but the investigation of the universe is far from over. The mystery of dark matter, the missing 27%, is still unsolved. What cosmic mystery do you want us to investigate next? Let us know in the comments below.